Yes?
Yes.
I'll go ahead and we'll do that then. Also, 3 people. Brittany Dodd, Matthew Allen, Kyle Poe. Are all 3 of you guys here?
Right here, buddy.
1, 2, miss 1. Okay, I'll need to talk to you guys after class just quick. Just come catch me.
Okay.
Beyond that, we'll pick up today right where we left off yesterday. I asked you guys to take a brief look. Question 2015, ice weight reduction diet. People thinking about chewing on ice. Of course, we know ice is cold. It takes calories to melt it. People think they can lose weight by eating ice. Well, it makes sense. You consume ice, burn calories, lose weight. Sure, bless you, bless you. So, bless you. Was anybody able to come to a conclusion as to whether or not this diet is a legitimate way to lose weight? You can take a pretty good guess because you don't see a lot of people chewing on ice to lose weight. So, we'll start. The question, how much ice would one need to counter 1,000 kcals? This is a food calorie. I think capital C is what it is, yeah. So we'll just use kcals, kilocalories. 1 kilocalorie is equal to 4,184 kilojoules. We deal with joules in this class, so we'll do that conversion right away. A couple other important points of information. The body temperature, 37 degrees C. Specific heat capacity for water, I didn't say water, but that is water. 4.18 joules per gram per degree Kelvin, or per degree C or Kelvin. And heat of fusion for water, solid water. 6.01 kilojoules per mole. So, how are we going to solve this problem? We have to do it in 2 steps. First, we're going to take some solid water out of the freezer, take some ice, and we got to melt that. That's where we'll apply the heat of fusion to our water. Then, I have to take my water at 0 degrees C, and I have to warm it to body temperature, 37 degrees, before it can get absorbed to my body. We are warm-blooded, so our temperature does not change. If it does, you're in trouble. So, first thing that you're going to do, we'll melt water. 6.01 kilojoules per mole. All right. Now, this is my heat of fusion for water, but I need to figure out how many moles of water that I have. So I'll say X moles of water. So that's the amount of energy that I'm going to consume during my melting process. However, I also have to include the notable specific heat capacity for water, 4.18 joules per gram Kelvin. Have to warm that 37 degrees. So I'll do the same thing as before. I'm going to need X moles of water, the same X that I have here. Same weight, just a different phase. I'm going to go ahead and warm it up. So, what am I going to do? I'm going to go ahead, I'm going to take my change. 37 degrees. We're all in Celsius here. And the next thing that I'll do is I'll say 4.18 joules, gram, and we'll just say degree C here. Same increment. Okay. Now I got a couple problems here. For starters, kilojoules, kilojoules, joules. What am I going to have to do to convert that to kilojoules? Divide by 1,000 or multiply? Divide. Okay, one other problem here. Kilojoules per mole is my heat of fusion. Specific heat capacity, The number that I've got is in grams. So, if I want to convert grams water to moles water, what do I have to do? Divide by 18. No, you got to multiply, because it's going to be 18 grams per mole. Okay, the hard part's done. Went through, did unit analysis, figured out everything. This big phrase here is going to spit out same units that I'm going to get from here. So, I'll write all this in terms of x. This one's easy, 6.01x. Oh, if you're also missing the unit, I'm sorry, x is in moles. So that's how the moles are going to cancel there. So, my next thing, I'm going to go through, I can do all this multiplication, and that's going to give me a number, 2.78, unitless times x moles. And then you can go ahead through, all you have to do is add these, it's going to give you 8.79x equals 4184. So, let's see here. If we're looking for the answer, we have 476 moles of water. (476 moles of water. We can convert that to grams. 8,577 grams, or 8.6 kilos. .6 kilos is a lot. So, if I want to eat an extra 1,000 calories a day, I'm going to have to go ahead and eat 17 or 18 pounds of ice to offset that. That's hard. So, the answer is, of course, a resounding no. Otherwise, it would be very, very easy to be very, very fit. So, if you're interested in losing weight, I recommend don't do ice. Stay away from the South Beach diet, too. All right. So, does anyone have any questions here? This is just basic unit analysis, application of specific heat capacity. We also use some other information given to us in heat diffusion. Okay. So, a special concern when we're thinking about delta HF, standard state, are aqueous ions. Now, we like to consider the proton. Just a hydrogen plus, one atom, no electrons, bare nucleus, as a standard reference point in thermodynamics for aqueous ions. Now, if I wanted to write an equation that's going to correspond to the heat of formation of this, it's going to look like this. You've got this in your book, I believe, on the top of the next page. Now, it's going to be very difficult for me to get at this because Dr. Horvath told you guys a couple of weeks ago, I can't isolate a single ion. I can't study just this reaction because this is just half of a full electrochemical reaction. You guys will learn about that a little later in the semester. But you can't go out and buy electrons. You can't collect them. You can't scoop them up. This is an incomplete reaction. It's only half of one reaction. So, it follows that we give this a number. Rather than say it's impossible to attain and leave all aqueous ions behind when we're talking about thermodynamics, we give this 0 for its heat of formation. So, follows, bottom of page 2018. Delta HF, standard state, for just a proton, aqueous, equals 0 for a solution at pH 0.00. Why is that? Why is the pH there? Remember what the standard state means. All my reactants and all my products are present. Partial pressure 1 atmosphere, concentration 1 molar. 1 molar H+, 1 molar hydronium ion, pH 0.00. That's extremely important to remember. I'd underline that a couple of times. These are standard conditions. It's going to come in very, very important when you guys are studying electrochemistry. Make sure that you remember that one. So, we now have a reference point for aqueous ions when we're talking about heat of formation. This is good. This allows us to study many other aqueous ions in solution by going through our reference point of 0. So, let's see here. Dr. Horvath makes another important point. Note that thermodynamic properties for aqueous ions are determined on a relative basis, relative to this 0 that we've given. So, as opposed to pure substances, negative S values for aqueous ions are possible. Let's take a look at table 1. Flip a couple pages forward. A great example, aluminum 3+, S0, absolute. Negative 321.7 joules per mole per Kelvin. It's hugely negative. Now, you'll see this for a lot of these aqueous ions that have appreciable charge density. Flip over to iron. I bet we'll see it here too. Iron 3+ aqueous, negative 315.9 joules per mole per Kelvin. You see the same thing for many other aqueous metal ions with appreciable positive charge density. Why is a really, really good question. I've got aluminum 3+. What's wrong with the formula that I have written there? I'm missing water, right? So I know that aluminum, a simple aluminum salt, say aluminum chloride, AlCl3, doesn't just dissolve in water to give me aluminum chloride. Sure, it gives me chloride ion, but it also gives me the appreciably acidic hexaaqualuminum 3. Now, aluminum grabs 6 water molecules. Water molecules, liquid phase. They're floating all over one another. They have a lot of freedom to move. However, when aluminum catches them, they lose entropy because they can no longer move as freely. They lose many degrees of freedom, and therefore S values for ions such as these are generally negative when you look at them in the table. So when you see those negative values, don't just say that's impossible, that makes no sense, Dr. Horvath made a huge error while he was writing this table. Think again and realize these are all relative, and compared to pure water, when I put aluminum ion on it, I order that water. Therefore, I bring its entropy down, and that's going to give me a negative standard state entropy value. So that's important to know that those are possible. Don't double guess yourself when you see something like this and you see a negative S value, because in aqueous solution that makes sense. These hydrates, they order water. And that is the reason why you see negative S values for aqueous ions. Some of them. Okay, so moving right along from there. The hydrated hydrogen proton. Now I know that if I take H+ and I put it in water, and I get hydronium ion. Now we know this occurs. We know that in water, we don't have any of this. None of this is floating around in water. We have H3O+. As a matter of fact, we don't know if H3O+ is the actual formula because those hydrogen atoms are jumping from water molecule to water molecule with extreme speed. We can't freeze it out because it's an ion. We can't get a crystal structure of it. We can only study it indirectly. H3O+ is generally the most widely accepted. But Horvath suggests a couple other ones. He says that it could be H5O2+, could be H7O3+, anything like that, because we're not exactly sure how that works. That's not of utmost importance to our class for now, but it's important to know that this is what happens in water, and the heat of this reaction, the enthalpy of this reaction, is also equal to 0. Because the second I put protons in water, they catch it. So this is another important definition that we've given to ourselves. Now, not only do we have this definition for the formation of hydronium ion, or the hydrated hydrogen proton, this also allows us to get at the heat of formation of hydronium ion. Now, this is actually very, very easy, because I know from Hess's law, I'm just going to add up heat of formation of my products, just one product. I'm going to subtract off the heat of formation of my reactants. So, let's see here. Delta HR, standard state this reaction, 0. I'm searching for delta HF, standard state of the hydronium ion. And then I'll subtract heat of formation for water, standard state, and I'll also subtract heat of formation of the aqueous proton, standard state. So, quick, fast, and in a hurry, somebody tell me what the heat of formation for hydronium ion is. I don't need a number.
It's going to be equal to the amount of water, so it's going to be negative 285 kilojoules.
Negative 280, yes, that sounds right. Yeah, about negative 280. So, it follows that using my reference point of 0 for this reaction and this reaction, I can very easily figure out the heat of formation for H3O+. That allows me to do very clever analysis of acidic and basic solutions that contain this species. So, he's got it right there, question and answer, towards the bottom of page 2019. Delta HF, hydronium ion, is equal to delta HF standard state, liquid water, negative 285. All right. So, you can do a similar thing. If you write out the heat of formation for hydroxide ion, or rather if you write out a reaction that gives you hydronium and hydroxide ion, you can solve for the heat of formation of hydroxide ion. Dr. Horvath does that for us. But you can't get it directly from the heat of formation because you have an electron stray. And that's never going to work. So, if you're looking for another example, that's another pretty good one. But let's do those questions towards the end of the chapter and move ourselves right along. Okay. So, we're given a reaction. Gaseous hydrochloric acid. plus liquid water react to give me hydronium ion and aqueous chloride ion. Okay. Question is asked of us. Oh, we're given some information too. Standard state, enthalpy of this reaction, negative 74.9. And that's going to be kilojoules per mole. Okay, so now I'm asked, despite the fact that this is on our table, I'm asked to go ahead and derive the heat of formation of chloride ion. Now, this is going to be really easy because the first thing that I'm to realize, heat of formation hydronium ion and heat of formation water are exactly the same. So I'm going to neglect those two right away while I'm applying Hess's law. So this is the equation that we're going to use to get at heat of formation chloride ion. I know HCl is a gas, it's a neutral species, for which it is easier to find the heat of formation in the standard state. You can look that up. That's going to be negative 92.3. So, distribute the negative sign, make sure I don't have my signs mixed up, and I realize that my heat of formation for chloride ion in the standard state is negative 74.9 less 92.3. Which I got to be negative 167.2. Kilojoules per mole. So this is once again taking advantage of our standard that we've developed for hydronium and H plus in an aqueous solution. And if you go ahead and you look up chlorine species, should be right here, aqueous chlorine, heat of formation, standard state, negative 167.6 kilojoules per mole. Pretty close. Good enough for us. All right. So, any questions there? Just applying Hess's law, cleverly realizing that hydronium and water are going to cancel when we're talking about this type of system. All right. So, we're given another reaction. Sodium chloride, salt, dissolving in water, to give us sodium and chloride ion. All right, so now I've got two ions here, sodium ion, chloride ion. Can't get at either one directly because once again, if I try to look at the heat of formation for sodium ion, I realize I'm going to have some electrons on the right Similarly, chloride ion, I'd have to have electrons on the left. So, I'm going to take advantage of the experimental measurement. As I dissolve sodium chloride, I find that, let's see here, delta HR is 3.8 kilojoules per mole reaction. So I'll write that down. All right. Now, sodium chloride is a salt. I know that I can get the delta HF for this pretty easily. We'll take that off the table. Pretty easily experimentally known. So, let's see here. Start writing Hess's law. Got it down over there. All right. So we've got our equation written down. The only heat of formation that I can very easily get at is the one on the far right. Let's see here. And that number is not written down by me. Let's take a look. Sodium chloride, negative 411.2 kilojoules per mole. So I'll distribute the negative. And then I'm going to realize chloride ion is just the conjugate base of a strong acid, HCl. So, what I'm going to do now is I'm going to go ahead and I'm going to take HCl gas, dissolve that in water to give me hydronium ion product and product chloride ion. From there, I'll be able to derive the heat of formation for chloride ion. But we already did that. I think these two questions are backwards. So, heat of formation chloride ion, negative 167.2. Now through experimental measurement on dissolution of sodium chloride, measurement of heat of formation solid sodium chloride, and being clever about one of our aqueous ions without using the table, we're in a position to solve. You can go ahead through, crunch the numbers. I got negative 240.2 kilojoules per mole. All right. So what we've done in this, 2 questions. Yeah, 3 questions. Right in the front, yeah.
If we hadn't done the previous problem, we would have had to do the previous.
You would have had to go and do it. That's why I think these are probably ordered a little bit backwards, because to get at this, you really have to use the hydronium ion, which is the internal standard that we've put in thermodynamics.
Okay.
Yeah.
For equations like these, your heat of formation is it always going to be positive for your products and negative for your reactants?
No, it doesn't have to be.
It doesn't have to be.
No.
Okay.
No, that just corresponds to bond strengthening or bond weakening
Right.
in comparison to its constituent atoms in their standard states.
So, but you still, I mean, for the change of H of F, that, you put the negative there because it was a reactant, right?
Yes.
Okay.
Yeah,
You
yeah.
can still change, you can still flip, but I was just wondering if,
Sure, yeah. This negative sign is always going to be here.
Okay.
Yeah, that's part of
the-
Hess's law.
okay.
Yeah, so that's always going to be there, but this could either be positive or negative depending on the nature of what HF or whatever reactants you have is.
Okay, thank you.
Okay. Another question?
I think that's my question.
Great. Okay. All right. So, everybody all set here? Good. Section 20.7. Quick and dirty. What we see here written is a reaction of elemental calcium, elemental sulfur, and elemental oxygen to give us calcium sulfate. We'll note that this corresponds to the standard entropy of formation for calcium sulfate. Yes. Now, does this reaction, the standard entropy of formation of calcium sulfate, correspond to the absolute entropy of calcium sulfate? Absolutely not. Can anyone explain why?
Is because calcium's not in its standard heat of reaction formula? Or maybe,
Well, we do see calcium there in the reaction that we have.
right. But is it, let me check me back. Okay, maybe not.
So it's not to do with calcium. This is going to be true of any reaction for which I write the standard entropy of formation. So, I'll realize. So what I'll do is I'll write down absolute entropy on a graph versus constituent or species. So, the first thing that I'll do is I'll take the absolute entropy of solid calcium added to 1/8 sulfur and 2 oxygen gases. Now, I'll look at the absolute entropy, solid calcium sulfate, the non-hydrated kind. So, this reaction, my little arrows here correspond to the change in entropy. But I'm on an absolute scale. So both of these entropies are above 0. This corresponds to the absolute entropy of calcium sulfate. And these are numbers that you can look up. I just drew a quick and dirty graph. But remember, the reaction that I've got here between constituent atoms of calcium, or constituent elements of calcium sulfate in the proper molar ratios, and calcium sulfate itself, is the change in entropy. These are not equal to the absolute entropy, because absolute entropy is a number that we can measure because we have a 0, that perfect crystalline solid at 0 degrees K. Though the cheap answer to the very last question would be yes, end of story. Okay, so don't forget this table, guys. It will be of immense use to you as we go on through chapter 21. Additionally, as we study electrochemistry, I don't know if that's chapter 22, you guys will be diving into that stuff as well. So, moving right along. Thermodynamics. Last chapter was the intro. Hopefully a lot of that stuff was review. It's all very important though, so we'll take your time on it. Now, thermodynamics. You guys hopefully know about Gibbs free energy. Gibbs free energy of a reaction is equal to the enthalpy of that reaction less temperature times the change in entropy of that reaction. Now, I can write this just as easily for the standard state. It's always important to remember that little degree symbol is of utmost importance when you guys are talking about what is actually in a reaction mixture. Do I already have products present? Am I only starting with reactants? Standard state, you've got them both. If it's not in the standard state, you might not. Now, let's see here. We know a lot of what Dr. Horvath is telling us here in the intro to chapter 21. Enthalpy talks about bond making versus bond breaking. Bond strengthening processes, bond making processes are favorable enthalpically and give us a negative delta H for our reaction, or delta H0, whichever. Entropy, which might be newer to some of you. Measured randomness. If I go from the solid to the gas phase, entropy increases. If I go from a shorter to a longer hydrocarbon chain, entropy increases. I have more degrees of freedom. These correspond to a positive change in entropy, which is favorable. It follows that negative Gibbs free energy values are favorable, positive Gibbs free energy values are not. Now, we're going to start coining the term spontaneous and non-spontaneous. I think we already did in the last chapter. But the spontaneous process, negative Gibbs free energy. That means it can go. Anti-spontaneous, non-spontaneous, whichever you prefer. Positive Gibbs free energy. Under those conditions, the reaction will not go. Cannot go. Why do we say can and cannot? We'll talk about that a little bit later in the chapter, rather than does or does not go. Okay, so you've got all your equivalencies there, all of your possibilities for delta H, delta S, resultant delta G. Hopefully you guys talked about that last chapter. If you're still having a little bit of trouble with it, Dr. Horvath really does a good job laying it out for you guys there. Now, thermodynamics is well introduced by using a phase diagram with which you guys are generally familiar. Water. There's a lot of it around. Now, a phase diagram, as Dr. Horvath says, is a G-state diagram. What is a G-state diagram? It tells us about thermodynamic stability. What can exist? What does exist under conditions of pressure and temperature that we name. Now, a lot of us are familiar with this half and this line corresponding to 1 atmosphere. That's only a very small part of the picture here. There's quite a bit to this phase diagram that we might have been missing in the past. So we can go ahead through it. Now, we see, of course, ice exists at low temperatures, just about any pressure. Liquid water exists, high pressures and high temperatures, compared to gaseous water and solid water respectively. And, of course, gaseous water will exist at any temperature, provided pressure is low enough. So, we'll go ahead and we'll study this, and we'll look at some associated questions. 21.1. Any point on line AD, how must the G's, of course these are relative, for liquid and solid water compare? Well, I see I've got ice 1. This is also solid water. It's one phase of solid water, and that's why it gets a special name. But we'll call it H2OS. So, line AD. G's for liquid versus solid water. How must they compare? Three options. Liquid's greater, solid's greater, they're the same.
For point AD, I mean line AD,
Line AD,
the G's would be the same
the same.
because both reactions would be negative G and it would be favorable for both of them.
Now, I think I understand where you're going. So, what was just considered there is, if I consider forming liquid and solid water, heat of formation, not standard state, because I'm increasing pressure along my y-axis, along this line corresponding to these conditions of temperature and pressure, those G's of formation, change in Gibbs free energy of formation, are going to be the same. That's why we use this quote G. I could say delta GF. Dr. Horvath likes to use quotation G, so we'll stick to that for now. But along line AD, solid and liquid water are in equilibrium. EQ, that means this well, I don't have a reaction here, but I can very easily make it one. That reaction that I've just drawn there is at equilibrium along line AD. So we'll write that. At equilibrium on AD. Same is true for all these lines, AB, AC. These are all equilibrium conditions between certain phases of water. Liquid gas, solid liquid. Okay. Oh, we're not done yet. How about the quote H's and S's? Which H value is going to be numerically greater? Which one of these phases has stronger bonds? Solid, absolutely. Stronger hydrogen bonding. So, this H corresponds to more negative, more favorable, so the greater H value goes to liquid water. Now, let's also consider the entropies. In which phase is randomness greater, liquid or solid water?
Liquid.
Liquid. Throw ice at someone, you'll figure it out fast. Don't do that. So once again, liquid water will have the greater value comparatively. Now, it's easy to see that this thing could be in equilibrium, and is, as a matter of fact, on line AD, because H, enthalpy, favors the stronger bonds, but S, entropy, favors greater randomness. So along those conditions, line AD at EQ. All right. Any questions on this one before we move along? Okay. Our next question. Look at line AD again. It slopes to the left. I know one person knows the answer. Why does it? I'm going to pick on you.
It's less dense. Ice is less dense.
Ice is less dense than water. You're drinking an iced tea. It's hot here in Florida. The ice always floats. It's not because of the sugar. So, I take a look at this. And I see, if I start with liquid water, 218 atmospheres, say negative 10 degrees C, and I reduce the pressure, I actually get solid water. So, I've reduced the pressure, therefore, by definition, making this substance less dense, giving me ice. So, line AD suggests, and we prove almost every day, ice is less dense than liquid water. The next question. Anybody been watching the hockey, by the way? Yeah? All right. I'm in Florida, so I don't know. It's been awesome. Those guys skate really fast, and ice is not that slippery. So, question 21.3. Is it possible to melt ice by applying pressure? Comment. Might this relate to ice skating? Comment. So, he sort of gives you a big hint there. You can, according to this graph. If I start with solid water, I apply a lot of pressure to it, I get liquid water. Somebody's waving at me back there. I have the unfortunate pleasure of knowing them. All right. So, might this relate to ice skating? If I take my body, 170 pounds, give or take, and I stand on two ice skates, which have a combined area of, say, what, 3 square inches or so, there's going to be a lot of pressure on those ice skates. And what that's going to do is that's going to create a very small line of liquid water on which an ice skater can glide. That's why these people move so darn quick, fast, whatever, both, on water, not on ice. Ice is slippery, but not as slippery as it is when you're wearing skates. Those of you that are bad at it know. All right. So, question 21.3 sort of answers itself. Again, just looking at this phase diagram from a thermodynamic perspective, it tells us a lot. So, line AB, a little bit more interesting. Have any of you guys worked with dry ice before? Solid CO2? Okay, so this is probably back in high school when you're first learning the definition of sublimation, right? Because you put dry ice on the table and it just gases up right away. There's a bunch of CO2. You never see liquid CO2 anywhere because at room temperature conditions, liquid CO2 cannot exist. It sublimes directly. In a similar fashion, at very low pressure, you can look at yours if my handwriting is too small or bad, or both. I have 6 milliatmospheres here. So if I'm below 6 milliatmospheres of pressure, and I'm also below the freezing point of water, I can create a situation that AB shows me, wherein solid and gaseous water are in equilibrium with one another. So, if I take this solid water here, and I reduce the pressure enough, I can cause sublimation. The opposite of sublimation, what is it? Don't look at the book. Deposition. Both are equally important. Good chemical methods to give you gases and solids of things that you want, and if you want them pure and uniform, deposition's a good way to do it. So, that's not a question in the book though. 21.4. What temperature, vapor pressure, and pressure of gas, pressure or external pressure of on water do we need for sublimation to occur? And why? I already gave you one answer. We have to be below the freezing point because line AB terminates at 0.01 degrees C. We'll talk about that point later. Now, what else has to occur? Maybe you guys learned about vapor pressure last semester. I have to have a comparatively low pressure of gaseous water in comparison to the vapor pressure of solid water at a given temperature. Vapor pressures are a function of temperature. We'll see that in a minute as well. We have the time. Okay. So, 21.4. We talked about temperature, vapor pressure, and pressure of gaseous water. All right here. And why? Well, first of all, my phase diagram tells me so. And secondly, what I know about vapor pressure also tells me so. We haven't gone over it this semester yet, but we will. All right, 21.5. In days of yore, when Dr. Horvath was young, this is on camera, washed wet clothing was air dried outside even in the dead of winter. Based upon phase diagram considerations, explain how this could be achieved if the outside temperature was less than 0 degrees C. Well, we're in the line AB category. We're talking about sublimation. So, I have cold, temperature less than 0 degrees C. Dry, low, partial pressure of water in the air. What's going to happen under conditions like that if I take a wet shirt and I pin it up after it freezes? Cold, low partial pressure of water. What's actually happening when those clothes dry out on a line in the dead of winter, where it's cold and dry? Sublimation is happening. I take a frozen shirt, I leave it outside, all that water actually comes off without evaporating. Goes directly to the gas phase and flies off with the dry water. This is also related to freezer burn. That's another question that we've got coming up. Okay. So, any questions about that? Sublimation. We'll talk more about vapor pressure later too. Okay. Next, line AC. At any point on this phase boundary, liquid and gaseous water are in equilibrium with one another. Very similar to line AD when we're talking about liquid and solid water, or line AB, talking about solid and gaseous water. Okay. Brief interlude to talk about the supercritical fluid, because they're really cool. So, 374 degrees C is the highest temperature at which I can have liquid water. At that point, no matter how much pressure I apply, I will never actually have true liquid water. This has been studied before. We have reactors that can achieve incredible pressures. We can actually make fake diamonds. So, what happens when I take super duper hot water and I apply a lot of pressure to it? Over 374 degrees C, over 218 atmospheres of pressure. We get what's called a supercritical fluid. Now, supercritical fluids are very, very cool because, first of all, they flow very, very well. Water flows with gravity, it flows over itself quite well, but you also have hydrogen bonds being made and broken consistently, so it flows slower than it could. Supercritical fluid doesn't have this problem. It's very interesting. There's a lot of thermal energy there. Additionally, all of the water molecules are in contact with one another, as in a liquid, but they behave as if they're in a gaseous phase. Supercritical fluid. Very interesting. YouTube it. There might be a cool video on it. I don't actually know. Okay. So, moving on from there, something a little bit more important or relevant to us. Point A. 0.006 atmospheres. Temperature, 0.01 C. I see a convergence point of ice 1, liquid water, and gaseous water. What's this called? Triple point. Because we have a unique condition where in liquid water, gaseous water, and solid water are all in equilibrium with one another. And these conditions are relatively easily approached in a laboratory. It's kind of convenient that water is easily studied as such. So, triple points are very, very interesting. 3 species in equilibrium with one another. It's also important to note, water has more than one triple point, as do many substances. So while I was talking about this, I realized I missed the point up here, where Dr. Horvath has written for you guys, ice 2. What's ice 2? It's still just water, but we've applied so much pressure to our solid water that we've actually caused those HO bonds to compress a little bit more and conform into a different crystalline structure that allows it to relieve some of this pressure. Now, if I take a look at point D, this is also a triple point for water. Because I have liquid water, ice 1, and ice 2, all in equilibrium with one another. I think Dr. Horvath mentions that on the following page. Yep. Now, we can go up a lot greater than 2,000 atmospheres of pressure. As it turns out, I don't know if ice 4 is the limit, but we found many different crystal structures for simple old water by just applying pressure to it. It reconforms itself to reduce space between molecules. All right, so that's triple point. Water has more than one of them. Many pure substances do. And that's good to recognize. There isn't just one between solid, liquid, and gas, but there's another one between solid, different phase of solid, and liquid. Okay. Couple questions. Just quiz our knowledge here. Question 21.6. Can liquid water exist at temperatures below 10 degrees C? Say this is 10 degrees C right here. Go up in pressure? Sure it can. Straight from the phase diagram. How about below 22 C? Got 22 marked off right here. Just keep going up in pressure. I'll note that point D, it gets close. It gets to equilibrium with solid, second phase of solid and liquid, but it'll never actually get there. So the answer is no for the second part. Why or why not? The data I currently have tells me so. Question 21.7. Would our world exist as we knew it if ice 1 was more dense than liquid water? So ice 1, that's just solid water, the stuff you put in your drinks. Well, what would happen in the wintertime up north, where lakes freeze over? What would happen to the ice if ice were more dense? It would sink. So, what would happen to a lake? It would completely freeze over. We would be stuck in an ice age from which we could not escape. And that wouldn't be good. So, our world would not exist as we knew it, or as we currently know it, if this little curve in the phase diagram did not exist. If water weren't awkward, we wouldn't be around. Okay. So, question 21.8. Freezer burn is caused by the fact that frozen foods are improperly packaged. Which are improperly packaged can dehydrate. That's better. Tell how freezer burn occurs. Hint, this involves sublimation. The answer is sublimation, which might surprise you. And so, you know, your fridge constantly recycles air. That's why when you open your freezer, there's generally no odor. Fridge is a little bit different, but the freezer recycles air. So, if I know these conditions must occur for sublimation, if I am constantly removing water from my atmosphere and freshening it with dry air, I'm going to constantly be trying to attain an equilibrium between the vapor pressure of solid water in your frozen food and the gaseous phase of water, which is going to be continuously created by sublimation. So, package your foods well, create an equilibrium inside your package of beef, chicken, whatever you've got in there, and you won't have freezer burn. It's from sublimation. Okay, so that's the phase diagram for water. I suggest you take a second look at it. It's good for this stuff to sink in. Any questions on those questions? 21.1 through 21.8. Okay, so start quick on vapor pressure. We got a couple minutes. All right. Vapor pressure of a substance. Dr. Horvath calls it a measure of the tendency of the liquid to evaporate as a function of temperature. That's a good definition. I also like to say the pressure at or below which a substance boils at a given temperature. So that's pretty much saying the same thing, whichever definition suits you best. Vapor pressure can be a little bit confusing, especially if it's only your first or your second time seeing it. So, take these to heart, especially Dr. Horvath. He'll be happier with that. So, we make the note, given that kinetic energy for a sample of matter increases as temperature does. We know that, solid, liquid, gas. The vapor pressure for any substance also increases. So, I know that as I increase the temperature of a pan of water, I increase its ability or its tendency to boil at a given pressure. That's changing temperature. And we're talking about that as a function of pressure, either with either. So, we take a look at water. Is it possible to boil water at 0 or 5 degrees C? Sure. Just need a super duper low pressure. You guys know this. If you put water in a vacuum chamber, it'll start to boil. Now, we also see temperature 100 degrees C, pressure 760. Well, we're not really we are given the unit, torr. 760 torr is 1 atmosphere. It follows that at exactly 1 atmosphere of pressure, water will boil at 100 degrees C. That's where we get that definition from. Now, if I take a look, as I lower that pressure, I lower the temperature at which water boils. Has anyone ever been to Colorado? Have you ever tried to boil an egg in Colorado? It takes about 4 hours. Because water boils at a significantly lower temperature at the low pressure, high altitude conditions of the Rocky Mountains, as compared to us at about 1 atmosphere here at sea level, close to it, I think we are. So, that's a good example. And we can take a look. Question 21.9, 21.10. We got time, good. Okay. So, consider going from solid to liquid water at 25 degrees C, 1 atmosphere. So I'm right about here. Oh, we'll circle it. Make a little star. So those are my conditions. Why is this process spontaneous? Well, because I know from my G-state diagram for water The only phase of water that can exist at these certain pressure and temperature conditions is liquid water. That's all I can have. And I get that from a G-state diagram, which is a thermodynamic stability diagram, as well as a phase diagram, which it's commonly called. Is it possible for this process to be anti-spontaneous at these conditions? So, what that means is it possible for me to make liquid water turn into ice at 25 C, 1 atmosphere? Well, we just kind of said it. The answer is no. Liquid water is the only stable phase of water at these conditions. Okay, so that's question 21.9. Hint, see the phase diagram for water. G-state. All right, we'll talk about question 21.10. Consider gaseous water to liquid water at 25 degrees C, 1 atmosphere. Is this process guaranteed to be spontaneous at these conditions? Is it possible for this process to be anti-spontaneous at these conditions? All right. Now, Dr. Horvath goes along, asks us a lot of questions. Okay. Now, we're sort of cheating a little bit because Dr. Horvath tells us 25 C, 1 atmosphere. So we'll go ahead. I will take the temperature to be slightly variable. Actually, we'll keep it at 25 C. All right. Now, if I'm in an air-conditioned room such as this one and I have glasses on, and then I walk outside to where it is very, very humid, my glasses are cold. Cold lens. What does that mean scientifically? Lower vapor pressure of water. Now, I walk outside. Muggy outdoors. Now, what does that tell me about my partial pressure of water in the atmosphere? High. So, those of you with glasses or that commonly wear sunglasses, what phenomenon do you see? Condensation. So, if I had combined these two conditions, I'll find that gaseous to liquid water occurs. But then, what happens as your lens begins to heat up as you're outside? All that condensation just goes away. If you're very, very patient and don't mind not seeing anything for a minute, you'll find this vapor pressure very slowly increases to the ambient vapor pressure of the temperature that is the outdoors. And then you'll find you're very easily able to remove that liquid water because you will have less than an equilibrium. You'll have driven the reverse reaction to occur, liquid to gas. So, I think on an old exam, Dr. Horvath asked the same kind of problem like this. If you're perusing through those, take a look at his answer. It was probably a little bit more concise than my own. So that's all for today. Tomorrow, more thermodynamics. Thursday, more review.